So this is for the first session of today. So our first talk is NetEdit, Network eBPF Orchestration Platform by team from Meta. And we have Prashant here who will be telling us about this work. So Prashant Kannan is a software engineer working in the host networking team at Meta Platforms. Prior to Meta, he was a tech lead at Brocade, focused on load balancing products. And Prashant has a master's in computer science from USC and a dual major in bioelectronics from BITS Pilani in India. I'll take it over, Prashant. Looking forward to your talk.
Hi, everyone. I'm Prashant Kannan. Thank you for coming to the non-AI talk, and so early in the morning. I appreciate your time here. So, along with all my co-authors here listed in the slide, I'll be talking about NetEdit, an eBPF orchestration framework that we've deployed across the Meta data center fleet. For background, Meta operates over 20 data centers with varying hardware configuration. Now, zooming into one data center, the picture in the top, we can see that we have thousands of services that run on a shared server pool. This is a diverse network. We have diversity in both hardware configuration and also service traffic characteristics. Now, how do you orchestrate this network for optimum performance? This is the problem we're trying to solve here. Thank you. So NetEdit allows service owners and network experts to collaborate together to optimize our network. Okay, let's look at a few problems first. The first one is from a physical network. How do you reliably tag every packet, even the ones at the very start of the connection, based on RTT? Now, why is this important? Switches can do preferential treatment based on the RTT. For example, do ECN marking. We talk more about this at our NSDA talk, where we've chronicled our DCTSP deployment experiences. Now, looking at one particular service, let's say service A, let's say it sees high ingress bursts, and this is impacting its performance. One potential option is to clamp the TCP windows and minimize and control the amount of data that's on the wire. By doing this, we have a theory that we could control the bursts and help improve the performance. This is a theory, right? How do you validate this? Can you run production experiments quickly and quickly try out this idea? Lastly, similar to this, you could have multiple tuning features that can coexist, even for the same service. Now, taking a step back, you have three kinds of things. You have features that are running across all the services at Meta. You have features that are custom tuned for some services. And lastly, you have experimental features that you want to quickly try out. So what you want is a platform that can give you high reliability and is also extensible. We saw a few problems. Now let's look at some potential solutions you can use to implement all this. The first one is you can make services call sets or copt. But this means that you have to build a library and deploy this with every service. You're also taking on a service dependency. You could also configure features through routes. But this means you're mucking with the routing table. And this is another dependency that we did not want to take. sysctls and kernel modules don't provide the right level of granularity we need. For example, how do you tag short RTT connections through this? How many of you have heard about eBPF here? Oh, great. Similar to the keynote talk yesterday, we find that eBPF provides us the right level of flexibility and the granularity that we need. For example, we can hone into specific packets in a given connection or take actions for every connection in the whole fleet. Okay, before we go to the design, let's quickly talk about some of the requirements that we had. First, we want to be very developer friendly. What this means is we want developers to be able to quickly prototype ideas, iterate on them, and safely deploy tunings to the whole fleet. We also want to abstract eBPF complexities to developers as much as possible. Second, we want to be highly available. Our goal is to be like the Linux kernel itself. This means if NetEdit goes down, we don't want to bring down the data plane along with it. The third is context-specific orchestration. To draw an analogy, think of it as the demand paging feature in the virtual memory. Can we load and attach programs on demand exactly where we need them? We want to minimize dependency. We don't want to depend as much on the services or the network to avoid tight coupling. Lastly, we wanted to have safe deployments. If NetEdit was to go down, we did not want to bring down the network with it. This means we wanted to have very good test coverage for both the programs and the kernel interfaces that we were using, and also have the right observability for us while we deployed changes. There's a lot in the slide, and I'm sorry, I'm not going to be able to cover all the details of all the abstractions. Please refer to the paper for the details. What I wanted to highlight here is NetEdit and its abstractions are in the middle of the figure. On top, we see things that NetEdit depends on from Meta's infra. For example, consuming policies, observability, and also knowing about what services are running exactly where. On the bottom, we see an important abstraction called the eBPF adapter. This is our view into, this is an abstraction for both kernel and the entire eBPF subsystem. Through the BPF adapter, we have something like a CRUD interface where we can translate high-level policies into actual BPF map state. We also abstract kernel differences. Different versions of kernels have different eBPF capabilities, and feature owners need not know about all this when they're developing a feature. Lastly, the on-demand feature. We want to be able to attach programs just exactly where we need it. In the next two slides, I'll talk more about some of the data plane ideas and a control plane idea in a bit more detail. Okay. I'll cover four key ideas of our data plane that we have in the paper. To do this, I'll take one example and walk through all the ideas. So within Meta, we use IP address as a proxy for distance. So by looking at the source and dest IP of a connection, even before the very first packet is sent out, you can figure out whether the packet is within the same rack or if it's going across geographic regions. Now, we have a separate feature called scope resolver that calculates the scope of every connection. And as you can imagine, you want this to run before any of the tuning features run. So the first idea is having determinism when we run BPF programs. We do this by creating BPF chains in any attach point, in any BPF attach point, where more than one program is supposed to run. Okay, we've computed the scope. Now, how do you make this available for all the programs that run? To do this, we use shared eBPF maps. We create maps that every program across attach points can look at and share data between them. Lastly, NetEdit itself is a user-based process, so it can go down because of us pushing new code or because of a bug. When this happens, how do we keep the data plane alive? To do this, we started pinning BPF programs and maps that way through a dedicated file system so that they're always available. The moment we started doing pinning, we kind of created a new problem for ourselves. Till this point, we had one version of program that was running that version was tied to the NetEdit instance. But now, programs can persist even longer. In our fleet, as you can imagine, we do have long-lived connections, connections that exist for days or much longer. In one case, we've even seen hundreds of versions of BPF programs on a same host. So what we wanted to go back to what we had before about having control over the versions. We wanted to have a single version of program per feature. To achieve this, we use BPF iterators. We can walk through every open connection in the host and apply a BPF program to determine policy and choose the right version of the program we have. We looked at some four data plane ideas. Now, in the control plane, I'm just going to focus on how we consume policies. NetEdit uses policies are authored outside NetEdit. We have a single central policy store so that the user intent is very clear. You can think of policies as a bunch of match action rules. The match criteria helps you say what is the service boundary and also what is the scope at which the service has to operate. The action is very feature specific. It can be about one or more parameters that the feature cares about. Different features consume policies at different intervals. It could be in the order of seconds or minutes. It's mostly the staleness guarantees that the feature has to provide. Okay, so we spoke about the policy store and policies. There's a policy engine running within NetEdit which consumes all the policies, and it also has a resolver that can get the state of the system right now. With both of this information, the policy engine can decide what set of policies have to be updated. And then it uses the CRUD interface I described before to program the BPF state. One last point is, I mentioned how the BPF adapter can do lazy attach. So together with now policies can change very dynamically, but the deterministic ordering that I mentioned makes sure that regardless of how policies change, when we run programs, they're always in a deterministic order. Okay. We looked at some requirements and a high-level design. Now let's see how different users of NetEdit actually end up using it. I'll talk about 3 classes of users. The first is service owners. Service owners care about network performance and reliability. The main interface they have is to the policy store. Through this, they can define their service boundary and configure one or more feature settings that they care about. The second group of users are network experts, you guys. Network experts typically care about quickly iterating on ideas and having safety when they're deploying features to the whole fleet. So development flexibility and having observability and safe deployments is something that this user group cares about. Lastly, infra engineers. Infra engineers manage the whole NetEdit and all of its abstractions on the whole fleet. So for them, minimizing dependency on the rest of infra and making sure the system is highly available is really important. In the paper, we talk about one interesting capability here called touchstone. Essentially, the problem is, I discussed how feature owners can quickly iterate on their features and do A/B experiments. But what about infra changes? To do this, we have a custom feature that's deployed to a selective set of the fleet, and through this we can try out any infra changes in this feature before we touch any of the actual production features. Okay, let's quickly look at some of the performance wins. I'll do this in 2 parts. First, I'll talk about some simple transport techniques and the kinds of wins we saw in the fleet as we deployed them. Next, we'll do the exact opposite. To understand the whole of NetEdit's impact, we will disable NetEdit totally, go back to kernel defaults, and see how the performance is at that point. The first feature is tuning the initial congestion window per connection. For short-lived connections, we saw a service latency win, and in one particular case, for a AI image generation service, we saw a 30% improvement in latency. The second feature is tuning receiver window, and doing this can help tame bursts. For a storage service, we saw 100% faster reads by taming the receiver window and controlling how much bytes we had on the wire. Tuning jumbo MSS helps us configure where helps us take on jumbo larger MTU for specific connections. By doing this, we saw an efficiency win on both the network and the host. For an ad service, we saw 6% improvement in the CPU utilization. Lastly, by configuring congestion control and building our own, we were able to significantly reduce retransmits and also see up to 40% improvement in latency, P99 latency, for user visible services. So these are a few simple features. So please refer to the paper for more description about both the features and the performance wins we had. We wanted to do the exact opposite, like turn off NetEdit. To do this, we picked a region, and across the entire region, we disabled NetEdit and all of its features for up to an hour. And this is what we saw. Looking at the network side, we saw high incast patterns, and at an aggregate, we saw a 10% drop in the aggregate throughput. At the host level, we saw high retransmits. to the point of seeing 29x increase in retransmit timeouts. Both of this correlated to services as well. For the metrics that they cared about, we saw a regression in QPS and also in read latency for different services. So through this, we were able to validate that NetEdit's performance, NetEdit and its tuning have a real-world impact in Meta's infra. Okay. What are the takeaways here? First, we've shown that we can run eBPF just like any other software within the Meta fleet. NetEdit and its abstractions provide the right level of glue that we need to make host networking as a service by itself. I covered two interesting aspects. One is about taking user intent and converting it into actual data plane function, and two, how we can provide consistency and predictability when we string together multiple eBPF programs and run them in our fleet. We hope that the scaffolding, we think that the scaffolding we've built would have to evolve as we take on new features. But we hope that the base can just be extended. Talking about scaffolding, all the kernel components that we've ever built have all been upstreamed to the Linux kernel community. Also, all the bugs that we've identified when we've deployed features, even they have been upstreamed. In the interest of time, I skipped a lot of details from the paper. For example, our deployment experiences, interesting infra and kernel bugs that we saw and how we fixed them. We also have a section about attach point selection. Two interesting examples from this are, by moving from one attach point to another, in one case, we saw a 200x improvement in performance. And in another case, we were chasing something similar, but we ended up breaking the feature. This is because we did not understand the kernel nuances around the eBPF attach point. Please refer to the paper for this and other interesting details. I think that's all I had. I'm ready to take questions.
Hi, Prashant. This is really cool. So for a question that I wouldn't be able to answer by reading the paper, if you're comfortable, can you say something about who you had to ask to turn off this feature in a particular region, or how did you go about choosing a place? Who did you have to check with?
Right.
The complexity of that process.
So I can talk about it at a high level. We did it by ourselves. And we did it because we made it as an independent service. So we had to give the right level of advance notice to all the teams. But we were able to create a site event and do this completely by ourselves.
Well, it's super cool work. I think in one way I think this is just a comment and questions coming in this, like you turning off NetEdit and seeing so much performance drop almost seems like a failure of this community to bring systems that the only way you can get performance is through fine tuning through eBPF hacks. But that's besides the point. The question I'm kind of curious about is, so your system does not look inside what the eBPF program is doing. Is that correct? Like you worry about attach points and version management, but like the internals of the eBPF program are like a black box for you. They could be doing anything.
Right. Let me first take on your comment.
Yeah.
I think this community is really great, right? But what you need is the ability to try out ideas, and that takes time. So let's say you come up with a cool idea and you upstream it. I'll probably have to wait for a few months to get my hands on it. But through BPF, I can try it out the very next day. And that's exactly what we're able to do. Now, your second question is about what does the system know about the features? Mm-hmm. It treats features to a certain extent as a black box, but then there are components that straddle different features. Like, for example, the scope resolver I mentioned is something that every feature kind of like reuses. But then there are pieces that feature owners have to, we provide the scaffolding and feature owners use those scaffolding to build their respective features.
Yeah, so I should have been clear. I guess the thing I'm kind of trying to get at is the composability of these eBPF programs. Like by the time a particular host is running, 15, 20, today it's 10, then if it becomes 20, 25, who's responsible for determining whether they compose well together? Is it like individual eBPF program owners? Will it be NetEdit in the future? Or how do you kind of view that?
So, yeah, we do that by dog fooding and trying things out much more in advance. So let's say you have those 15, 20 programs. We have ways to test all of them together.
But this is a combinatorial problem at this point, right?
Right. So we don't have an explosive number of features. We have a double-digit number of features, and it's something that we are able to solve today.
Got it.
And in the future, if it's like really that explosive, we'll have to rethink how we're going to do this.
Got it. Okay.
Following up on that, is it something that you kind of test at feature introduction, like, look, I'm going to introduce this feature, will it compose well with all the other features that I have? Like, is that like how you roll out new features? Or?
So you have a feature, you have an idea. At that point, you are not fully thinking about all the, you don't even know what are all the things that you can interact with, right? So you'll probably experiment with that standalone. But once you want to deploy this, we have a tier where we can like A/B test different things, where multiple sample features are turned on and we have policies. So through this, we can make sure if there is anything that goes wrong. The interesting thing is it's deterministic. We'll know exactly what can run before and after. So we'll be able to debug it through that. But despite all this, we've seen cases where we've seen issues in production. At that point, we need the ability to quickly roll back and then go fix things.
So I'm Daisuke Botanic from Kyoto University. So thank you for the talk. So I'm curious whether the control plane of NetEdit interact with other container orchestration systems such as Kubernetes, and if yes, so how much the NetEdit control plane is so integrated to the other orchestration container orchestration systems or cloud orchestration systems?
So NetEdit is within Meta. We have an equivalent of Kubernetes called Twine. So NetEdit closely integrates with Twine and also with our configuration management system so that it can understand what services are running on a given host. But we've used more of a pole model, not a direct dependency. So if NetEdit goes down, those services will not go down, but the tunings will.
Thank you.
Hi, I'm Ashwin from IIT Bombay. So during your experience with all of this work, did you come across or did you want a hook somewhere in the kernel network stack which is not there today? Like, would you like a new hook to come up in the kernel network stack?
Oh, all the time. So most of the things that we've upstreamed are things that we really needed, and we ended up building it with help from our kernel team. For example, we wanted to like build our own custom congestion control algorithms. For that, we built this structops interface that helps us like deploy full congestion control algorithms. And then the iterator that I mentioned. There are a bunch of other things that we did, but it's a constant thing. Any new idea we have, we might need a new BPF capability.
So quick follow-up to that, like, do you see a future where the entire stack it's programmable by itself? Like you can program anything and everything across the entire stack. Like, would you see something happening of that sort?
There is a cost associated with the flexibility, so it's a fine balance between the two. So for example, whenever possible, we try to not use per packet programs because they are expensive. The map lookups, like there was a workshop talk about it. It's an expensive thing. So a few points are really interesting where you can do most of the functionality. Like for example, if you can operate on every connection, that's something we can do today. We can also like implement like full like kernel module equivalent algorithms. I think that has a lot of flexibility in the future. There might be other parts of the kernel where we want to build our own full custom implementation. So there are pieces like this, but making the entire kernel customizable, I think, has its own costs.
Okay, thank you.